Take a look at the opening paragraph that I have. I told you last week your concepts of your trig functions, your 6 trig functions, those are going to be introduced to you 3 ways. The first way was last week, taking a look at an angle that's in standard position. You pick that point P, and we define those 6 trig functions in relation to the x-coordinate, the y-coordinate, and your r value that you got. The second way that we're going to take a look at these 6 trig functions are in terms of lengths of sides of a right triangle. The final method that we'll use later on, we'll take a look at the relationship between your trig functions and what we call the unit circle. Some vocabulary that we need to get out of the way first, when talking with the sides of a right triangle, all of us are pretty familiar that the length, or the side of the triangle that has the longest length, which is usually right across from the right angle, we call that the hypotenuse, and then the other 2 sides we call the legs, other side. So assuming that's my right angle, the side across from the right angle, which ends up being the longest side, we call the hypotenuse. And the other 2 sides, we just refer to those as being legs. Now, in terms of the trig functions, we get more specific. What we consider as the opposite side or the adjacent side has to do with the angle that you're talking about. Those are going to change. The hypotenuse, however, that will always be the longest side. It's never going to change. That side remains hypotenuse. The words opposite side and adjacent side, those 2 words refer to the other 2 sides, but which one's opposite and which one's adjacent, again, like I said, will be dependent upon the angle that you're talking about. So if I were to relabel this triangle ABC, and I say let's just pick on angle A. Okay, the hypotenuse stays the hypotenuse; it doesn't change. Now, if I say what's the opposite side, you think what's the opposite side in terms of angle A? So what side is across from angle A? This side would be considered the opposite side. And then through the process of elimination, then, this guy over here is the adjacent side. Okay? And then if I were to back up and say, well, let's pick on angle B, this still is the hypotenuse, but now this becomes the opposite side, and through process of elimination, that would be the adjacent side. So those 2 words are dependent upon whatever angle it is that you're talking about. Now that you have that vocabulary down, hypotenuse, opposite side, adjacent side.
If you do angle C, are they both adjacent
well,
then?
No, we really don't talk about the right angle itself. It's always going to be one of the other 2 angles. Okay. Yes. One of the acute angles. Once we have the vocabulary down, then we're going to redefine our 6 trig functions. Now, the earlier definitions are still there. Y-coordinate divided by r for sine, x-coordinate divided by r for cosine, but now we can redefine these 6 trig functions as the ratio of the lengths of those sides. So sine of an angle A will be now known as opposite side over hypotenuse in terms of the lengths of those sides. Cosine, adjacent over hypotenuse, tangent side, opposite side over adjacent side. And you know, folks, I always just remember those 3, and we all know then the reciprocal property kicks in for the other 3. All right? Does anybody remember a little saying or a word used in high school that helped you memorize these over here? SOHCAHTOA. And now you know why or where that's coming from. We're picking off those letters, oops, not that one, this one, that one. Helps you memorize those 3 on the left. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So it's a quick word or phrase helping you remember the 3 on the left. And then once you know those, you can use the reciprocal property to get the 3 on the right. Okay? Let's take a look at our first example. It says, given this situation, here we're given the 3 sides of this right triangle, 7, 25, and 24. Come up with the sine, the cosine, and tangent values for angles A and B. So on the left-hand side, let's come up with the sine of A, the cosine of A, and the tangent of A. We know that the sine of an angle is opposite over hypotenuse. So here we are at A. What side would be the length opposite from A? 7 or BC. So yeah. So we're looking at 7 over hypotenuse, which is 25. So the sine of that angle is 7/25. The cosine of the same angle, A, well, if opposite side is 7, hypotenuse is always 25, the adjacent side would have to be 24/25. And then again from angle A, let's do tangent of that angle. Opposite over adjacent. Opposite would be 7. Adjacent would be 24. So those are your 3 solutions there. Does your sine divided by cosine still apply here? If you were to take 7/25 and divide that by 24/25, do you get 7/24? Absolutely. This fraction divided by this fraction is the same as multiply by the reciprocal. Your 25s would cancel each other out, and you would be left with 7/24. So that property also still holds. On the right-hand side, let's go ahead and do the sine, cosine, tangent for angle B. And now in terms of angle B, opposite side would be 24, hypotenuse 25, so this is 24/25. Cosine of B, 7/25. And the tangent of angle B, opposite 24 over adjacent 7, 24/7. Now the reason why I actually walked through all of those, both for angle A and angle B, is take a look at the left side and the right side. If I were to call 2 of those out, take a look at this. It looks like the sine of angle A is the same thing as the cosine of angle B. And it looks like the cosine of A is the same thing as the sine of B. And tangent's another story when we start talking about cofunctions. But I just want you to focus on sine and cosine for the minute. What relationship does angle A and angle B have with one another? What's true about A and B, those 2 angles?
They equal 90.
They have to equal 90, which makes them complementary angles. So the next property that I have covered up that you've just discovered is that the sine of an angle is equal to the cosine of its complement. And that's the relationship between sine and cosine, and then it's also the relationship between tangent and cotangent. So we call this relationship the cofunction identity. So basically all we're saying here, and I like to keep in mind that since we're dealing with cofunction identities, that's where we're dealing with where these prefixes are coming from. Cosine, cosecant, and cotangent. Tangent and cotangent are cofunctions. Sine and cosine are cofunctions. Don't get these mixed up with your reciprocal rules, right? Because that's a whole other different thing going on there. Sine and cosecant are reciprocals, but sine and cosine have this cofunction identity going on. So basically all we're saying is the sine of an angle is equal to the cosine of its complement. The cosine of an angle is equal to the sine of its complement, and it's true for all pairs of cofunction identities. So how could we use this? Well, we'll start off with a very, very basic example, which will lead into, actually, you're going to end up solving your first trigonometric equation today. But given this situation, write each function in terms of its cofunction. So how could I write cosine of 52 in terms of its cofunction? Well, we know that the cosine of 52 degrees equals the sine of what? Its complement, 90 minus 52 degrees. So the cosine of 52 would be the same thing as the sine of what? 90 minus 52, which is 38. So to double check, making sure your calculator is in degree mode, it should be true that the cosine of 52 degrees, my calculator is probably not in degree mode since it resets all the time. Let me change that to degree. Look at the cosine of 52 and look at the sine of 38. End up giving you the same value, which they're supposed to. Cosine of an angle equals the sine of its complement. We'll do one more. B. Tangent of 71 equals the cotangent of 90 minus 71. So the tangent of 71 would equal the cotangent of, how many degrees would that be? 19? 19 degrees. Now, if you're asking me, how would I check that on my calculator? Because I have a tangent button, but I don't have a cotangent button. The tangent of 71 gives me 2.9, etc. How could I somehow come up with cotangent of 19?
Isn't that tangent of -1?
Reciprocal of the tangent. Absolutely. Reciprocal. So just simply say, calculator, what is 1 divided by the tangent of 19? Get the same value. So yeah, exactly right. In some cases, you got to use the reciprocal property to enter those functions into the calculator. I'm not sure if the x to the -1 works.
No, it comes out 8. If you do second tangent, it comes out 86.
No, I didn't mean inverse tangent. No, that's a whole other different story. I meant the x to the -1 button over there on the left side of your calculator.
Why doesn't it work?
It's not, I guess, for that purpose, for trig relations. I don't know. I didn't try it yet. Let's try. What do I want to do here? Inverse or reciprocal of 1 tangent 19. So what if I said tangent 19 to the -1? Yeah, that does work for reciprocal. There's a big, you're going to learn later on what those yellow commands are. These guys right here, inverse sine, inverse cosine, inverse tangent, and the -1 notation there is different than what that -1 notation is there. Do you remember when you did functions in college algebra, you used that -1 notation for inverse function? Just simply had a different meaning, same symbol, but in math sometimes we use the same symbol for many different things. Now let's use our cofunction properties, identities, to solve your first trig equation. Here we're trying to come up with the value of x or the value of theta. And theta we use as a variable, meaning unknown angle measure. Come up with the value of theta that would make this a true statement. And what you want to try to do, folks, with these problems is get the same trig function on both sides of the equation. So on the left I got cosine. On the right I got sine. But we now just learned that there's a relationship between sine and cosine using our cofunction property. You have your choice here. I can change the left to the sine function, or I can change the right hand side to the cosine function. You just want to make sure you have the same trig function on both sides of the equation. So the cosine of this angle in parentheses, right? Theta plus 4 degrees, folks. That whole thing is just a single angle measure. So we know that the cosine of that angle is the same thing as the sine of 90 minus that angle. And now I have the right-hand side of that equation. Did I lose anybody there? On the left-hand side, I simply said the cosine of this angle is the same thing as the sine of its complement. And now we got to use the distributive property. We'll distribute the negative through. So on the left-hand side, we have sine of 90 degrees minus theta minus 4 degrees equals the sine of 3 theta plus 2 degrees. And now that I have the same trig function on both sides of the equation, what has to be true in order for this equation to be a true statement? The two angles have to be the same, right? So what's in parentheses on the left has to equal what's in parentheses on the right. So 90 minus theta minus 4, and those are in degrees, has to equal 3 theta plus 2. So we'll solve this equation. I'm going to add theta to both sides, giving me 4 theta on the right. 90 minus 4 is 86, and I'm going to subtract 2 more off of that, giving me 84. So theta is 21. There's the value that makes that statement a true statement. If you would have changed the right-hand side to a cosine situation, you're still going to end up with the same answer. Doesn't matter which side you change into which side. So go ahead and try letter B on your own. Change one side to the other using your...
I get 90 again?
Excuse me?
I get 90 degree again?
90 means they're complements of one another. 90 is coming from the fact that the two angles add up to give you 90 degrees. So if you know one angle, the other one has to be 90 minus that because they are complements of one another. So I'm going to choose to change cotangent to tangent. I'm going to leave the left side alone. So we have tangent of 2 theta minus 18. I'm going to say that's going to equal. Now the right hand side, I'm going to change this cotangent in terms of tangent. So the cotangent of that angle equals the tangent of its complement. And then the rest is just like the last problem. On the right hand side, we'll go ahead and use the distributive property. I mean, I can go ahead and set them equal to each other right now. Now that I have the same trig function on both sides, that means that 2 theta minus 18 degrees would have to equal 90 minus the quantity theta plus 18 degrees. Distribute the negative through. We get 90 minus theta minus 18 degrees. I'll add theta to the left, giving me 3 of those. And what do we get there with, well, we're going to add 18. Looks like they cancel each other out, and we're left with 90, telling us that theta has to equal 30 degrees. Right? Do all right?
I didn't get that.
Uh-oh.
I don't know.
I didn't get that.
Did you find a mistake? Look for your mistake.
I did the other side.
The other direction.
Yeah.
Next item, we have what are called special right triangles. And there is a reason why we call them special right triangles. The one on the left is known as the 30, 60, 90 right triangle. And the one on the right has 2 names. The one on the right, we can call it the 45, 45, 90 triangle. Or it's also known as the isosceles right triangle. Why? Because it has 2 sides equal to one another. Okay? And I'll show you the relationship a way a little bit different than what your textbook is showing you right here. It might not be as obvious as to what they're showing you with these 2 pictures. I'll let you know where this one comes from, or what it's all about. If we were to start with an equilateral triangle, equilateral means all 3 sides are the same length. So let's say we start with one of those, where all three sides are x units long. Equilateral. Well, one property about an equilateral triangle is every single angle is how many degrees do you think? If the sides are equal, the angles are equal, and if you want them all to add up to be 180, they all have to be 60 degrees, right? So all three of these are 60 degrees. Now, if you and I construct or draw what we call the altitude from this point, meaning I'm going to drop a perpendicular segment down, there's a couple properties about this segment. Number one, it will always cut the bottom side, this guy, in half. So if the whole thing was x units long, now we have x over 2 and x over 2. And not only does it act as a segment bisector, guess what it does to that 60-degree angle at the top? It also takes that 60-degree angle and cuts it into 230s. Right? Now I'm going to pull one of those right triangles out. Well, on the left, on the right. So let me find the right triangle here. Let's just pull out the left side of that triangle, where we know this is 60, we know this is 30, and now this is a 90-degree angle. We have the hypotenuse being x. We have the side across from the 30 being x over 2. And how could I get the missing side? What could I use to get that third side of the right triangle? Pythagorean theorem. Absolutely, right? C squared equals a squared plus b squared. So it has to be true that, I'm going to just momentarily call it y. We got to know, or we know it's true, is that y squared plus x over 2 squared equals x squared. And we'll solve this for y. We're going to go ahead and subtract x over 2 squared from both sides. Well, that becomes what? That becomes x squared over 4. I'm going to take it to the other side. So far we have y squared is x squared minus x squared over 4. And before I can put those two together, I've got to get a common denominator. So I'm going to make this 4x squared over 4. And then I'm going to combine like terms, and that's going to give me that y squared is equal to 3x squared over 4. And now let's go ahead and take the square root of both sides, and I get y. Technically it would be plus or minus, but since I'm dealing with a length, I can't have a negative length. So when we take the square root of both sides, you take the square root of the top, you take the square root of the bottom, and when the smoke clears and the dust settles, we will end up with x root 3 over 2. Okay? That's what y is equal to. So I'm going to go back up here and relabel this triangle x over 2 times root 3. It's just another way of writing x root 3 over 2. And now the relationship is jumping out at you. It turns out, and this is always true with a 30, 60, 90 situation, whatever the length of the hypotenuse is, whatever it is, the side across from the 30 is always half of it. So if this is 10, this is 5. Okay? Also, notice that the side across from the 60-degree angle is always the shorter side, meaning the side across from the 30, times the square root of 3. So you could label that side, knowing that the hypotenuse is 10 and that the other side is 5. What do we got here? We would have 5 root 3. Right? That's where this picture is coming from. They're just showing you that if the hypotenuse was 2, the side across from the 30 is half of that, and the side across from the 60 will always be the short side. In this case, it's 1 times the square root of 3, which would just be the square root of 3.
So that's only work with 30 degrees.
Only 30, 60, 90 triangles. Only 30, 60, 90 triangles. Now on the right-hand side, we have what's called the isosceles right triangle. And a property that if you had some type of high school geometry, maybe you learned it in another class, one property about an isosceles triangle is not only are two sides equal, but also the angles across from those got to be equal. So in terms of an isosceles right triangle, these two angles need to add up to be 90, and if they're both the same, it forces them both to be 45 degrees. Okay? And the property that we're seeing here, as I'll spell out where it's coming from, we call it the isosceles right triangle property. We know that these are 45. And we know that if those two angles are equal, then these two sides have to be the same. And again, we simply use the Pythagorean theorem. Call this y for the moment. We know that y squared has to equal x squared plus x squared. Y squared is equal to 2x squared. And then to get y by itself, we'll take the square root of both sides. And when I take the square root of 2x squared, I end up with x root 2. So y is now labeled x root 2. So the moral of the story is this: if you have an isosceles right triangle, these two legs are going to be the same value. And how do I get the hypotenuse? I simply take that value and multiply it by the square root of 2. That's the relationship between those two triangles. Now the homework problems that you'll be given is you'll be handed 30, 60, 90 triangles, or you'll be handed 45, 45, 90 triangles. And you'll know certain parts or pieces, and it'll be your job to come up with all the other missing parts. And we'll do one of those together when I'm done with the lecture. Any questions on what these two are saying? Those two properties. I like taking time to showing you where certain things come from, because maybe it helps you to remember the relationships. When I taught high school, I always told my students, I always keep in mind 3, meaning 30, 60, 90, root 3, the 3's are together, and over here we have two angles that are the same, and that's how I know that that's a 2 under the radical and not the 3. 3 goes with 30, 60, 90, and the root 2 goes with the 45, 45, 90. Okay.